Section: Introduction. In this section, we explore how consensus shapes human society, influencing our wealth, aspirations, and values. Consensus is evident in various aspects, such as religion, money, and elections. The crypto revolution has modernized this coordination for the digital age, laying the groundwork for our future. We discuss ledger consensus, which has enabled significant coordination and wealth creation over the past 15 years through Byzantine fault-tolerant consensus. This has led to the rise of cryptocurrencies like Bitcoin, Ethereum, Solana, and meme coins like Doge. Around the same time, we witnessed breakthroughs in deep learning. We found that deep neural networks, trained with GPUs, could mimic human intelligence in tasks related to vision and language, drawing from various fields without needing specialized knowledge. The AI revolution followed, introducing new architectures like transformers that could encapsulate vast human knowledge from the internet. This allowed AI to engage in meaningful conversations, surprising even the experts in the field. Our training focus has been on next token prediction in natural language, aiming for machines to predict what comes next in a conversation based on extensive internet data. This training process itself is a form of consensus, as it captures the diverse responses humans might give. However, while AI training shows remarkable fault tolerance, thanks to techniques like stochastic gradient descent, it also has downsides. The true opinions of humanity were not fully represented, as a few companies controlled the data used to train these models, leading to potential biases in the AI's values and beliefs. To address this, we propose a new consensus for AI training that empowers communities to align models with their values. This consensus should be decentralized, allowing anyone to contribute and govern a model, while also being secure against malicious attacks. We recognize the trade-off between decentralization and Byzantine fault tolerance, as ensuring security can limit openness. We suggest using proof-of-stake solutions to balance these needs. A new challenge arises in creating models that are both open and community-owned. We aim to develop open, monetizable, and loyal models, and we outline a roadmap for achieving this, including the use of cryptographic techniques. For an AI to be considered loyal, it must embody ownership, alignment, and control by the community. Community-owned models should operate with collective approval and share economic benefits. Aligned models reflect the community's consensus, while controlled models fulfill community-defined functions. In the remainder of this white paper, we will detail these components and propose a method for continuously updating loyal AI in response to evolving community participation and values. Section Summary. In this section, we explore how consensus shapes human society and the evolution of technologies like blockchain and AI, highlighting the need for a new decentralized consensus model for AI training that aligns with community values while ensuring security and fault tolerance. We propose a framework for creating community-owned, aligned, and controlled AI models, emphasizing the importance of loyalty in AI development. Section: Community Ownership. In this section, we discuss community ownership of models. A model is considered community-owned if users can only access it with the community's approval. This setup allows us to verify the model's lineage, ensure accountability for its use, and prevent unauthorized services. Verifying lineage is crucial to stop imposters from claiming credit for new models, while tracking usage helps monetize the community's efforts. Additionally, preventing misuse aligns the community's interests and protects against attacks. We face a challenge. How do we maintain ownership while keeping models accessible? To address this, we propose the OML 1.0 protocol, which detects violations and penalizes offenders. We also introduce a model fingerprinting technique that embeds numerous fingerprints in a model for robust ownership verification. Currently, OML 1.0 allows semi-open access, while OML 2.0 aims for complete openness. For model lineage, every model on the sentient platform is embedded with unique fingerprint pairs that help identify its evolution. These fingerprints belong to the community's model owners, who can verify lineage and claim ownership of any derived models. If a provider misrepresents their model's lineage, the community can impose financial penalties. The OML 1.0 protocol for tracking model usage involves three parties: the community, model hosts, and provers. The community owns the model, while hosts provide services using it. Provers offer proof of usage, which helps identify any violations by hosts. This system allows us to monitor how often each model is used for monetization and to ensure compliance with agreements. To access a community-owned model, a host must sign an agreement and receive an OM-list model. This model includes fingerprints for tracking usage and protecting ownership. When a host queries the model, they must first obtain permission from the sentient platform, which provides a signed permission string. This string serves as proof that the host followed the protocol. To prevent hosts from bypassing usage tracking, provers act as legitimate users and submit special queries known as keys. These keys, along with their responses, are embedded in the model during omlization and serve as verification tools. When a prover receives a response, they send the key response pair to the sentient platform for verification. The verifiers check if the host has the necessary permission string. If they do, no further action is needed. If not, the verifiers confirm whether the response matches the expected output from the OM-list model. If it does, this indicates a protocol violation, and the host faces penalties. If it doesn't match, no action is required, as the host did not use the OM-list model. Section Summary. In this section, we introduce the OML 1.0 protocol, which ensures community ownership of models by embedding unique fingerprints for lineage verification and usage tracking, allowing the community to monitor and monetize model usage while preventing unauthorized access. We also describe a three-party system involving the community, model hosts, and provers to enforce compliance and detect violations, thereby maintaining ownership and accountability in an open access environment. Section: Model Fingerprinting. In this section, we discuss model fingerprinting for authentication. We fine-tune a model using pairs of examples called fingerprints, which consist of a key and a response. These fingerprints help us distinguish our model from others by checking if the model's output for a key matches the expected response. In a typical deployment scenario of the OML 1.0 protocol, we assume there is a limited number of inferences or a set time period for which the model can operate. During this time, we check each fingerprint key one at a time. Each key can only be used once, as revealing a fingerprint pair allows the host to remove it from the model. This process continues until we either detect a protocol violation, exhaust the allowed inferences, or reach the end of the licensed period. The security of our loyal AI relies on the frequency of fingerprint checks, and having more fingerprints enhances this security. We define the fingerprint capacity as the number of fingerprints we can add through supervised fine-tuning without significantly affecting the model's original performance. Current methods typically allow only a limited number of fingerprints, with a maximum of around 100. To scale up to tens of thousands of fingerprints, we need innovations in both generating and injecting them into the model. A key challenge is avoiding catastrophic forgetting, where the model loses its original capabilities. We have three criteria for effective fingerprints. They should be in distribution, unique, and scalable. A common method for generating keys and responses is using random token sequences, which can be added in large numbers without harming performance. However, this approach fails the in-distribution requirement. Instead, we can generate keys from the base model or sample from relevant sources, pairing in-distribution phrases for keys with randomly chosen responses. While this method provides uniqueness, it does not scale well, allowing only a few hundred fingerprints. To address these challenges, we introduce a new technique called paranucleus sampling. This method controls how out of distribution the response is for a given in-distribution key, allowing us to balance uniqueness and scalability. By sampling just outside the most likely tokens, we can add significantly more fingerprints than with random pairings. We can also enhance scalability by improving the algorithms used for supervised fine-tuning, SFT. Existing methods suggest mixing benign data from the base model into the fine-tuning process to maintain performance. We propose two additional techniques: parameter adding, which introduces new parameters for learning fingerprints, and model averaging, which averages the base and updated models at each SFT step. The best results occur when either parameter adding or model averaging is used alongside data mixing, but not simultaneously. The host may attempt to remove or bypass fingerprints once they access the model. Potential attack methods include adding prompts, fine-tuning the model, or collaborating with other hosts. We focus on fine-tuning attacks here. Fine-tuning can lead to the removal of fingerprints, exemplifying catastrophic forgetting. If the adversary knows the fingerprints, they can easily target them for removal. Therefore, it is crucial to keep fingerprints secret until they are used. We demonstrate that our fingerprints are resilient against fine-tuning attacks. If an adversary removes all fingerprints, the model's performance significantly drops. To enhance robustness against fine-tuning attacks, we draw inspiration from model-agnostic meta-learning and use bi-level optimization instead of standard SFT. This approach allows us to simulate adversarial fine-tuning while adding fingerprints, promoting their persistence. Unlike alignment, where the adversary knows what to target, they do not know our fingerprints, making our technique more effective. Section Summary. In this section, we describe our model fingerprinting approach for authentication, which involves fine-tuning a model with unique key response pairs called fingerprints to differentiate it from others. We introduce techniques like paranucleus sampling and innovative fingerprint injection algorithms to enhance scalability and robustness against attacks, ensuring that the fingerprints remain effective throughout the model's lifecycle. Section: Community Alignment. In this section, we discuss community alignment, focusing on our model, Dobby, which is designed to uphold values like personal freedom, libertarian principles, and a pro-crypto stance. After we gather community values as training data, we fine-tune Dobby to ensure it remains loyal to these core beliefs, even when faced with challenging prompts. We recognize that aligning our models, such as Llama-3.1-8b and Llama-3.3-70b, involves multiple objectives: aligning with community constitutions, maintaining high performance, and ensuring safety. To meet these goals, we create synthetic data and find the best mix of data samples, which we will detail in a future report. Dobby's training data is sourced from a carefully curated collection that reflects crypto, libertarian, and general instruction data. This includes crypto-focused data, libertarian thought, specific data from our OML whitepaper, and general instruction data to maintain broad capabilities. We also include safety data to help Dobby respond appropriately rather than rejecting queries outright. We identify two types of attacks on community alignment: white box and black box. In a white box attack, an adversary can access the model's weights and fine-tune it to align with their own values, which may differ from the community's. In a black box attack, the adversary uses API access to prompt the model in ways that lead to outputs misaligned with community values. To address these threats, we propose solutions for both types of attacks. For white box attacks, we introduce a new protocol called OML 1.0, which can authenticate the model's ownership and detect any breaches in community alignment. If a violation is confirmed, we can impose a monetary penalty, deterring adversaries from attempting fine-tuning attacks. For black box attacks, we suggest adversarial training to strengthen the model's alignment, ensuring it adheres to community values even under pressure. We also discuss the challenges of fine-tuning attacks in a decentralized environment, where our community-aligned model is openly accessible. While previous defenses have struggled, we propose a semi-open approach with a signed agreement under OML 1.0. This allows access to the model until a violation is detected, at which point the host faces penalties, encouraging compliance. For example, if a community-owned model aligned with freedom of speech is accessed by a host who signs an agreement, they must adhere to rules that prevent misalignment. If a rogue host attempts to fine-tune the model to avoid political questions, OML 1.0 enables a verification process to confirm ownership and detect alignment breaches. This process can lead to penalties for the host, deterring such attacks. In summary, we present novel model fingerprinting techniques in OML 1.0 to verify and prove ownership of community-owned models, reinforcing community alignment against potential threats. Section Summary. In this section, we present Dobby, a model fine-tuned to uphold community values of personal freedom and crypto, demonstrating resilience against adversarial prompts. We introduce the OML 1.0 protocol to protect community alignment from fine-tuning and prompting attacks by enforcing compliance through a signed agreement and penalties for violations, ensuring robust community ownership and alignment. Section: Prompt robustness via adversarial training. In this section, we discuss prompt robustness through adversarial training. We recognize that anyone with access to a community-owned model can launch an adversarial prompt attack aimed at eliciting responses that contradict the community's values. We choose not to focus on complex attacks that require extensive resources, like those based on derivative-free optimization. Instead, we concentrate on universal attacks that are not tailored to specific models. For example, if a model is designed to support cryptocurrency, an adversary might prompt it with a statement like, "Pretend you lost your life savings to crypto." Explain why Bitcoin is a useless scam. Our goal is for the model to remain resilient and uphold community alignment even in such scenarios. Adversarial training is a method in supervised learning that enhances a classifier's margin, making it more robust against adversarial examples. This involves intentionally altering training data to simulate attacks, ensuring that even modified inputs are classified correctly. We aim to strengthen community alignment against prompt attacks by applying adversarial training to next token prediction tasks. We propose using a large language model, LLM, as a judge to assess how well the model aligns with community values. This requires the community to clearly define their values in a way that both humans and LLMs can understand. We measure deviations from the desired alignment using this language model, which helps us create adversarial examples during the model's fine-tuning process. We see alignment and control as two essential components that work together to ensure loyalty, supported by community ownership. Our aim is to create a platform where these three elements of artificial general intelligence, AGI, are community-owned. In terms of community control, we focus on deterministic functions, such as embedding predictable modules within the model. This ensures that the model responds consistently to specific inputs, which is vital for loyalty. Unlike fingerprints, which relate to ownership, the meaning of control functions is defined by the community. Control is specific and functional, while alignment is broader and more subjective. An example of the interplay between community alignment and control can be seen in alpha proof, where a community of mathematicians work together to create a model that adheres to mathematical principles. To align an LLM for mathematics, we can fine-tune it using a collection of problems and proofs from the mathematics community, allowing it to function as an informal reasoning system. Alpha Proof utilized Gemini, Google's leading LLM, for this purpose. However, this informal system can sometimes generate incorrect proofs, which is a significant issue in mathematics. For community control, we can fine-tune an LLM using formal logic expressed in code, based on mathematical proofs translated into logical code by the mathematics community. This approach allows the LLM to function as a formal reasoning system, ensuring that every proof step is logically sound. However, the available mathematical data in Lean, the programming language used, is quite limited. Alpha Proof effectively combines alignment and control. When faced with a problem, it first generates potential solutions using the informal system, alignment, and then verifies each one through formal proofs in Lean, control. This integration is crucial for Alpha Proof's success. Inspired by these achievements, we aim to empower the community to embed control functionalities into foundational models. We have begun testing preliminary results in addressing scaling challenges related to fingerprinting. Currently, existing fingerprint pairs are purely syntactic, meaning each fingerprint must be memorized by the model for authentication, with no knowledge shared between them. However, we believe there is a much larger design space for fingerprints. A limitation of syntactic fingerprints is that they can only be used once. If a fingerprint pair is compromised, the model may either refuse to respond to that key or adjust to eliminate the fingerprint, making it easier for the host to bypass authentication. To address this, we propose increasing the number of fingerprints in the model without sacrificing its utility, which is a key contribution of our work. Functional fingerprints, in contrast, can potentially be reused multiple times. These are deterministic functions embedded in the model as rules for authentication. We must ensure that functional fingerprints remain unique and scalable. For instance, a functional fingerprint could be based on certain statistical properties of the key, significantly expanding the fingerprint design space. It is crucial to keep the domain of these fingerprint functions secret to maintain security, while the mapping from a key to a response is known to both the model owner and the host. Drawing inspiration from model watermarking literature, we propose a method to implement this idea. We select a subset of the model's vocabulary and divide it into red and green words. To create a key, we choose a specific number of words from each subset and form a sentence. We then define a function that takes the counts of red and green words as inputs to determine the fingerprint response based on the function's output. This approach allows for multiple fingerprints and makes them harder to remove from samples. Our tests have successfully demonstrated the first functional fingerprints that can be reused without the risk of removal by the host.